Hello, my name is Ben Phillips and I'm a PhD student in the Department of Geography and Planning at the University of Liverpool and the Marine Physics and Ocean Climate Research Group at the National Oceanography Centre. This presentation will introduce how computer models can be used to simulate long-term coastal evolution under various coastal conditions. This presentation will introduce COVE, a two-line model designed to handle more complex shorelines in terms of their shape and the way in which humans interact with the coast. COVE is a two-line shoreline evolution model, where the two lines represent the coastline and the cliff line. The model is designed to be applied at spatial scales of kilometres to tens of kilometres over seasonal to millennial timescales. Coastal change is driven by gradients in waves generated alongshore sediment transport according to the Coastal Engineering Research Centre equation displayed on screen, which has been modified to account for sediment density and porosity. A key novelty of COVE is a method in which the model builds the coastline. Coastal cells are built by projecting cell boundaries seaward until they intersect, starting from the most concave seaward cell. The order in which cell building proceeds is numbered. When cell boundaries intersect, the mean orientation of contributing cell edges determines the direction in which the projection continues. Resulting cell geometries are either trapezoids, triangles, or polygons. This approach provides a more realistic simulation compared to previous models, where coastal cells could not accurately handle complex shorelines. It also allows a user to simulate human interventions such as beach mega-nourishment, which often complicate the shape of the shoreline. COVE still makes some assumptions which are common in one-line shoreline evolution models. The depth parallel contours shown on screen imply that cross-shore sediment transport acts to maintain a constant shore face slope, and offshore waves are transformed to nearshore conditions using linear wave theory. Many models of a similar type have only one line, which represents a coastline. COVE gives a user the option to specify a cliff line, which is able to represent either a fixed or evolving cliff line. In COVE, the cliff line and the coastline interact to determine how wide the beach is locally. Eroded cliff material is provided to the adjacent beach and causes the shore face to advance. Cliff erosion is controlled by beach width, since a wider beach provides energy dissipation and protection from approaching waves. However, a narrower beach deprives the waves of sediment and materials needed to cause cliff erosion. This can be seen in the upper diagram where a critical beach width is illustrated, the point at which cliff erosion will be most severe. COVE requires offshore wave data, which for the purposes of this model is defined as the wave conditions received at the bottom of the shore face, which are unaffected by refraction, shadowing, and shoaling. This can be obtained either from a wave buoy or preferably from modelled coastal area predictions of wave conditions, for example from SWAN or WaveWatch 3. COVE is also capable of using a bimodal or bidirectional wave climate to represent coastlines where waves coming from multiple directions have an impact on longshore sediment transport. The transport coefficient K may be modified to account for the size of beach material. Calibration of this coefficient can be made from estimates of bulk alongshore transport or by calibration against a historical record of coastal change. A digital elevation model provided by means such as light detection and ranging, also known as LiDAR, is required to allow the identification of the coastline and the cliff line, which can be fixed to represent hard defences such as sea walls. A minimum beach width can also be prescribed to simulate groin fields. LiDAR or Google Earth satellite imagery can also provide a means of validating the model against historic shoreline recession. COVE calculates alongshore sediment transport and a resulting coastline position change by following the loop illustrated. A wave is sampled from the assigned wave data and transformed to breaking conditions. Having constructed the grid cells to represent the shoreline, and the height and angle of the breaking wave is used to calculate the alongshore sediment transport. At this point, any additional sediment from cliff erosion is used to determine the gain or loss in volume for each grid cell and the resulting shoreline position change. This process repeats based on a specified time step, typically a day, for the specified model runtime. The model is able to reproduce the northwards migration of a large coastal foreland called Benacre Ness in Suffolk. It is called Benacre Ness because it used to sit in front of the Benacre estate, but has migrated northwards and now stretches across the frontage of Kessingland. It has been estimated to extend northward at rates of 20 to 50 metres per year, despite the locally established view that alongshore sediment transport is directed from north to south. Wave data from the southward wave buoy, located in 20 metres water depth, suggests that this stretch of coastline experiences a bimodal, bidirectional wave climate, with waves approaching out of the English Channel to the south and the North Sea to the northeast. If fed directly to COVE, this results in high angle wave instability that is not observed on this stretch of coastline. An AWAC wave buoy located at 7 metres depth tells us that these dominated wave modes are rotated to a lower angle of incidence in the near shore. So for this experiment, a similar lower angle bimodal wave climate is used. To reduce uncertainty in the transformation of waves to nearshore conditions using airy wave theory, it is important to use wave conditions near the depth of closure, which represents the most seaward point at which there is no significant change in elevation of the seabed. COVE shows Benacre Ness migrating northward at a rate of 20 to 30 metres per year in accordance with historical observations. It also shows the landform becoming elongated over time. COVE is an exploratory model for longshore coastal evolution, able to simulate human intervention with the coast, such as nourishment to build out the shore face, and represent hard defences or evolving cliff lines. The model is currently being developed to include a cross-shore dimension to simulate landward migration of gravel barriers under sea level rise in future wave climates. Coastal evolution models provide critical information for coastal managers to manage and plan for low-lying coastal communities, where the current shoreline management policy of hold the line is unlikely to be sustainable in the long term.